So, hello everyone. Good afternoon. My name is Vivek.Jaiswal, and along with my teammates vrushan.patil and aditya.tambe, we have worked on a project titled A 5-Stage CMOS Ring Oscillator Design and Simulation in 180 Nanometer Technology. So, this was done under our professor Akhil Masurkar sir, and under his guidance, we have completed this project. And this was completed in Vidyanangan Institute of Technology. So moving ahead, we will talk about the abstract. In this project, we designed a simulated five-stage CMOS ring oscillator using the Cadence Virtuoso tool and the GPDK 180 nanometer technology library. The circuit was powered at 1.8 volts and the simulation confirmed a stable oscillation frequency of about 2.4 gigahertz. The waveform analysis also showed that expected odd harmonics, proving that the oscillator worked as intended. This establishes a solid foundation for analog and RF circuit integrations. So moving ahead, we will be talking about the introduction part to introduction to this project. So this is a oscillator is one of the most fundamental circuit in the integrated electronics. It consists of an odd number of inverter stages connected in a closed loop. Each inverter added a phase delay, and when the total delay results in 360-degree phase shift continuous oscillation is achieved. The oscillation frequency can be estimated using the formula F is equal to 1 divided by 2n tau d, where n is the number of stages, tau d is the per stage. Our design uses 5 inverter stages to achieve these oscillations and verify its behavior in its simulations. So moving on to the next slide, we have motivations and challenges regarding this project. As a CMOS technology scales down into the nanometer region, it faces several challenges like increased leakage current, reduced voltage, headroom, and process variations. This effect make it difficult to design circuit that are both fast and power efficient. Hence, we need to robust oscillators design that can maintain stability, performance, and efficiency even in smaller technology nodes. Our goal was to achieve that the balance through optimized transistor sizing and circuit layout. Moving ahead, we have the literature survey. So traditionally, Dennard scaling guided CMOS evolution, reducing size, improved speed, and power efficiency. However, as we move to the submicron technologies, leakage power and device variability becomes the major concerns. For oscillator, the Barkhausen criteria defines the condition for the sustained oscillation. The loop gain must be at least 1 and the total phase shift must be an integer multiple of 360 degrees. We referred to several IEEE and IRJET papers to compare to LC oscillators and ring oscillators and found that the ring oscillators are ideal for one chip application due to the simplicity and area efficiency. So the next part is methodology, which will be explained by my teammate Rushan. So hand over to Rushan.
So, methodology. Our methodology is followed by a standard custom IC design flow. We begin with a schematic design, then processed it to a layout creation, post-layout is extraction, and simulated through Cadence Virtuoso. This flow ensured that our simulation reflected realistic silicon behavior, including parasitic effects. Next, circuit design. This circuit consists of 5 CMOS inverter stages connected in a loop. An inverter is made up of one PMOS and one NMOS transistor. To maintain a 50% duty cycle, the PMOS was made wider than the NMOS to compensate for the lower hole mobility. In our design, the PMOS has a width of zero point 0.2 micrometers and a length of zero point 0.3, while the NMOS has a width of zero point 0.1 micrometers and the same length. This balance ensures equal rise and fall time for the output waveform. This is the circuit diagram. Next, layout and verification. After completing the schematic, we designed the physical layout for one inverter and replicated it to form a 5-stage ring structure. The layout was optimized to minimize parasitic resistance and capacitance. We performed design rule checking and layout versus schematic verification, both while passed successfully. The total area layout was about 1.45 square micrometers, making it very compact and efficient. Simulation results. In the transient analysis, we observed a stable oscillation with a rail-to-rail voltage swing from 0 to 1.8 volts. The oscillation period was approximately 0.42 nanoseconds, corresponding to a frequency of 2.4 gigahertz. Fast Fourier transform analysis of the wave. waveform confirmed a strong odd harmonics, which are expected from a near square wave output. This validates that the theoretical operations of the circuit. This is the result of our output. Next, power analysis. We measure dynamic power consumption by integrating the current drawn from the supply. Because the circuit continuously switches, most of the power is consumed in dynamic and not in static. At gigahertz frequencies, the power consumption falls within the milliwatt range. This trade-off between speed and power is typical in oscillator design. Achieving higher frequency naturally requires more current. Now, for the next part, I'd like to call Aditya.
Key findings. Our final results show a frequency of 2.4 GHz, a propagation delay per stage of about 42 picoseconds, and a power consumption in the low milliwatt range. The output waveform had a nearly perfect 50% duty cycle and rail-to-rail swing. This result proved that the design is not only fast but also well balanced, making it suitable for integration into a high-speed system like phase lock loop or true random number generation. Next, conclusion. To conclude, our five-stage ring oscillator design in 180 nanometer technology achieved high speed and stability with excellent area efficiency. The circuit followed a complete design flow from schematic and layout to post-layout simulation, ensuring accurate real-world performance. This design provides a strong foundation for future analog and design and digital appliances such as log generation or frequency. Future scope. For, for future work, we plan to perform process voltage and temperature variation analysis to test circuit robustness. We also intend to carry out phase noise and jitter characterizations, which are important for communication circuits. Additionally, by introducing current stepped inverters, we can convert the circuit into a voltage controlled oscillator for use in phase lock loops and security oriented true random number generators. Acknowledgement. We would like to thank the Department of the Electronics and Computer Science at Vidyalankar Institute of Technology for providing access to Candice Virtuoso and Spectre tools. A special thank to our guide, Professor Akhil Masukar, for his valuable insights and guidance throughout this project. And the last reference. Our reference include IEEE Solid State Circuit magazines, IRGET papers on CMOS oscillators, and the textbook CMOS VLSI design by Harris. These sources help us understand both theoretical and practical aspects of oscillator design. The final closing will be done by Vivek.
Thank you for watching this presentation on our 5-stage CMOS ring oscillator design. We hope this explanation helps you understand how efficient oscillator design can bridge the gap between the theoretical models and the real integrated circuit performance. Thank you.